So great, so welcome back, everyone. So last Thursday was the first real quiz. I think the average grade on the quiz, averaging over everything, was like 91%, and this is okay. This is probably matches around what the average grade at the end of the semester will be. So I think that's okay. A number of you made kind of some small mistakes. I think if you just made one small mistake, I wouldn't kind of sweat it too much. They'll probably average out over the course of the semester. Occasionally you make a small mistake. It might look big on one quiz, but over the 6 quizzes, if you don't do that, so that often it's probably not too bad. A number of people had, I think if there's one thing that was a little bit more common mistake, it was the conditional probability question. So where there was a table with, so the probability of Utah and BYU scoring above or below 30 points, maybe that hit a little bit too close to home. So you know, if that's the case, a lot of people put in the joint probability instead of the conditional probability. So please, so kind of review that. If you have questions on a particular question, please ask me or the TAs. We sometimes reuse versions of the question, so I don't like to post too much, you know, so on public forums, but we're happy to explain stuff if there's something that you that you didn't understand what the right answer should have been. So hopefully also this gives you a kind of perspective on what the quizzes are going to be like. I think this was a fairly representative quiz. The average time, or the median, I think they gave me the average time to completion was about 20 minutes. So I think that seems this seems reasonable as far as the length of the quiz. There were very few of you who ended up going up to the last some amount of time, and I, you know, if you do that, that's fine. I know some of you are double checking everything until the very last minute, which is, you know, great. So I don't see going up to that last time as necessarily being a problem. So we are going to, let's see, where are we? If you look on the schedule, there's one thing about the office hours. One of the Zoom office hours for Hao Cheng it had a password on there we forgot to link to. There's no longer a password on the Zoom meeting, so it should work now. If that was an issue. Okay, so apologies about that. So I think this is kind of a good time to kind of ask and get feedback now that the first homework is almost due. Are the timings of the office hours seeming to work okay? Are there any kind of things that can be in general?
There's a lot on Monday and Tuesday.
Yeah.
So I tried to get my homework done in advance. So it was like,
okay.
Yeah.
Oh, so you'd rather they were even more spread out, actually.
At least like one was on like Thursday.
So okay. So I will talk amongst the TAs and maybe we'll do that. So great. And I'm always available after class. I don't have anything, I make sure I don't have anything scheduled. I'll stay here or in the courtyard if we run out of time. I'll try and stay as long as there are questions. So as well. But yeah, sometimes it's nicer with the TAs. So I'll see about that. I saw a few other nods in that direction. So okay, great. And then I guess as you saw, the first homework is so due today at the end of the day. Kind of don't forget to turn in the first homework. Okay, and the late policy on it is if you turn it up between 0 and 24 hours late, you lose. You lose 10%. You lose 10 points out of 100. If it's up to 48 hours late, you lose 20 points out of 100. Okay, so please see if you can turn it on time. That's great. But if you need an extra day or two for you just didn't schedule enough time, then you have a little bit of slack there. And the second homework is ready. We'll post it probably later today, but I guarantee it'll be posted by Thursday. Then if we look at the schedule, we're going to be kind of finishing up the probability kind of fundamentals and background today. We're going to be talking about some concentration of measure bounds, which I think will be usable ways of applying the central limit theorem. And then this will kind of give you a sense of how these things work, and they will be kind of implied and kind of referred to in the rest of the class, which is based on this idea that we have this data drawn IID, and we'd like to get more and more data to get better and better estimates of these things. And this should give us a sense of how that works. There's more stuff in chapter 2, which we are not going to cover. So if you kind of find this fun and interesting, want to see some more examples of how these things are useful, and some kind of simple algorithms based on sampling to approximate things, you can kind of explore on your own after the stuff that we cover. But we just aren't going to go into all the detail in this course. Okay, so let's go and get into it. I want to try and go through 3 bounds and a number of examples, and your next homework, you will have to kind of work through some similar examples yourself. So I think it'll be useful to try and go through this as we can. Let's see. And so we talked, there were 2 main kind of ideas that we talked about in class on Thursday last week. One, I'll just quickly write this up here. The central limit theorem, I'm going to have n random variables, x1, x2, up to xn, and they're all drawn IID from some fixed but unknown distribution f. And I'd like to do something like estimate the mean of this. So what I do is I create a single random variable, x bar, which is the average of all of these random variables. Okay, and I know that each of these random variables has an expected value of mu and a variance of sigma squared. Okay, and the central limit theorem tells me 3 things: that the expected value of x bar is the same as the individual random variables when I take the average. This should be straightforward linearity of expectation. So it's a good estimation of the expected value of f. The variance of x bar is the variance of x divided by n. So as I get more observations, the variance kind of is decreasing. I get a better and better estimate. This is kind of the second key. And then it kind of converges to some sort of normal distribution with this same mean and the variance decreasing at a squared event. Okay, so it's converging to a normal distribution, and what converges mean is a little bit fuzzy, and it will kind of depend somehow on what we know about this sort of distribution f, right? So what we know about f will allow us to say something more specific about this convergence process. Okay. And then the second important things was the, actually, let me just do this on a new page, was this idea of probably approximately, so correct. Okay, and this is kind of a little bit of a mouthful, so people often just say this is so pack bound. And this is kind of the way that these notions of how well we've converged are typically measured, right? I mean, there are a lot, I mean, in machine learning and data mining, how they typically are, in statistics and probability theory, there's a lot of other notions of so this convergence, and we're typically talking about a X bar, and remember, we're considering how far is it from the mean of X bar. Okay, we typically want to understand the error, the difference from the mean. And so we'd like to, and we'll say this difference, will usually, to simplify things, this is not always the case, to simplify, we'll often look at the absolute value of this difference. And we'd like to say, well, it's going to be, it's bad, you know, it's far from the mean. X bar is far from the mean of X bar if this difference is greater than some parameter, so epsilon here. And we'll think of this as like an error tolerance. Okay, so we've got, we have some, so we have some expected value of X bar, and there's some kind of probably unknown sort of distribution. Okay, so this is some unknown distribution F, right? That's for X bar, right? Remember that when we went back here, we had a distribution F for each of these Xi's, each of the individual random variables, but X bar is a different random variable, and it has its own probability distribution, but notably has the same expected value, but it's tighter. It's got more concentrated, right? And that's what's going on here. So this is a distribution of X bar, and we'd like to understand the error tolerance, so we can go out some distance, epsilon in either direction, and look at kind of the area, kind of this distance here. This is our error tolerance. We say if it's within this error bound, it's good, right? If it's further than that, it's bad, right? We want to say it's outside of the error tolerance, right? And this is a probability distribution. So sometimes when we actually make an observation of X bar, which is a bunch of observations of the individual Xi's, and then we average those together to get a sample mean, or a sample other kind of estimate of something. Well, sometimes it's going to be outside this tolerance because there's a random process going on here. So we need to we can't just say, well, it's good or it's bad, but there's a probability associated with that, right? So we wrap this in a probability that the error that the random variable is greater than the error tolerance. The probability than this, and we want to set this less than or equal to some other parameter, so delta, right? So this is the second term here, and this will be the probability of failure, right? Generally failure, but the probability we're outside the error tolerance, right? And so this corresponds with this area kind of in this tail, right? So what's this, if I integrate under this green curve here, it should integrate to 1, right? It's a probability distribution, and the integral outside the error parameter is corresponding to delta. So I'd like to, and I phrased it this way. So if you look at that this error is greater than epsilon and the probability is less than delta, I phrase it this way. So I want both epsilon and delta to be small, right? I could have flipped them around. I could have flipped one of the inequalities so that I, wanted the values to be large. It's easier to, I think it's easier to think about consistently. We want both of these sort of error parameters to be small. Okay, so the error tolerance and the probability of failure, and this is this probably approximate, so correct kind of way of phrasing stuff when you're thinking about randomized observations of the data, or that you have a randomized algorithm that sometimes something goes bad with, and it doesn't necessarily get the exact right answer. So, okay, so this is probably approximate correct, and we're going to look at some specific ways of trying to get bounds that look something like this. They're not always going to look exactly like this, but I'll try and phrase them in this, close to this form. Sometimes they won't have the expected value. I know the error will only be on one side. And sometimes we'll want bounds that will ask you a question that doesn't have the expected value, the absolute value. So then, but then I'll convert them into this so that I can apply the generic bounds we talk about in this course. There are quite a few ways to get bounds that look exactly like this or something like this, and mechanisms, and we're not going to go through all of them. There are whole textbooks on this sort of stuff. We're going to go through a lot of the core ones, and I'm going to try and keep them as simple as intuitive form as I can. Okay. All right. So the first approach we're going to talk about is going to be the simplest, I think the simplest, most basic form of this bound. And we're generally not going to prove them, but I'll give kind of something close to a proof for this first one called the Markov inequality. Okay, and we'll go through them, and then we'll go through some examples of using them. And what I want you to get away is kind of how to use them and kind of what to look for in how to use these things. And this will kind of give you a sense of how this works. Okay, and so the important part in this bound is I'm going to have one random variable, in this case, x, and I'm going to know that I'm going to know something about the expected value of x, and I'm going to know that x is greater or equal than 0. These are the properties I need to know about this random variable, and for the different bounds we'll talk about, we're going to have different known properties about it. We'll always need to know the expected value, but the other things we know about it will get slightly more complex as we go on. And that will make the bounds a little bit a little bit more complicated, but more powerful as well. Okay, and so this inequality says that, well, then we can, so yeah, for any alpha greater than 0, parameter alpha, we can say the probability that x is greater than alpha is going to be less than or equal to the expected value of x divided by alpha. Okay. So this is the key bound. So it kind of looks like this probably approximate correct. This right-hand side here, the expected value of x divided by alpha is my delta here. And I don't quite have a difference from a mean here, but I could write this if I wanted to as I could instead set epsilon equal to alpha minus the expected value of x, and then I can write and delta equals, yeah, like expected value over alpha, and I could write that the probability of x minus expected value of x is greater than epsilon is less than epsilon x divided by epsilon plus expected value of x, which is equal to my delta. Okay, so I could write it in this form, although we typically use it in this form. Okay, so in order to work with these bounds, you will get some information about a problem, and you'll need to do some kind of little bit of algebra sometimes inside this, inside the probability. If I have an equal then less than, then I can do some algebra here, and this affects it on the outside, right? So I did a substitution of epsilon equals alpha minus expected value of x. And so then I can substitute epsilon in on the right-hand side here, right? And but that's epsilon. In order to do that, I need to subtract epsilon x from both sides, including on the left-hand side. Okay, and that's how we get something that looks like the difference from the mean. Now, this one does not have an absolute value around it. The other ones will write them with absolute values. They don't always do that, but this is truly a one-sided bound in this case, and we'll see a little bit why that is. And then that changes a little bit what this right-hand side looks like, what equals to delta here. Okay, so this is the form of the bound. Let me give a little bit of intuition about why this is true, and that'll help give you some kind of sense of what is going on here. And then we'll go through an example of applying this, okay? The way I like to think about this is that there's a tray. Okay, there's a tray, and someone's put some like a pile of Jello on the tray, right? And I know what the mean is, right? I know what the expected value, and so I kind of actually, I'm balancing this tray on my finger, right? Remember, if I balance a distribution at the mean, right, then I can, then it will stay on my finger. If you're a waiter or waitress and you're carrying a tray of drinks, as long as the center of mass or the mean of all the weight of the drinks is under your hand, it's not going to tip over. Okay, and if I make my hand really small to a point that's in my finger, it has to be exactly on the mean here. Okay, my camera seems to be frozen here okay, so it has to be exactly on my mean, on my finger. Okay, and so this is known to us. We're given the expected value, right? So this is one of the properties that we are given here. We get the expected value, so we know the mean has to be right here. The second property we have is that x has to be greater or equal to 0. So what we're going to say is that, well, this point here is 0. I know that no mass goes left of this point. The tray has a left endpoint, okay, and none of the probability is less than that, okay? But now I did not restrict the right endpoint of the tray. So it could go out pretty far. I haven't said how far out to the right it's going to go. And I want to say, well, the probability that it is greater, I'm going to pick some value alpha out here, some value alpha. What's the probability that it's greater than alpha? What's the probability that the mass is greater than alpha out here? Okay, well, in the first green Jello kind of distribution I've drawn up there, there's no mass greater than alpha. There's none of it, because I drew kind of a fairly symmetric tray here. But I know the expected value needs to be there, and I know it can't go left of so 0. So I kind of want to think of what is the most mass I could put out to the right of alpha, and I won't put it too far right of alpha. Let's think of a different distribution here with some blue Jello. Okay, where I'm going to put a pile of blue Jello here. The area under here is, area under here is going to be equal to, this area is delta. Okay, so I have a delta probability just past this alpha. Okay, how much can I put out there so that the mean stays at 0? Well, the right thing to do then is to put all the rest of the probability kind of exactly at 0. Like, think of it being exactly at 0 here, so that the rest of the probability is exactly at 0. So I can't move it any further left, but I have to balance the expected value. Okay, so I have to solve for keeping the expected value fixed, and I have 1 minus delta. So then if delta fraction of the mass is right of alpha, then this is 1 minus delta fraction of the mass. Towards the expected value, its term is 0, right? So if I get the expected value of x is going to be 1 minus delta times 0 plus some delta fraction times alpha, right? The rest is at alpha. Okay, and so I can say, well, this is kind of the most extreme case, and then I can solve for the value of delta. Delta is going to be equal, because this term goes away, expected value of x divided by alpha. Oh, that's exactly what I have for delta here, expected value of x divided by alpha. So this is kind of a proof of what's going on here, right? So if I know a lower bound in the distribution and the mean, I can get a sense for any parameter alpha, how much mass can be out there. If I put more mass further to the right, well, then the expected value would have to tip over. Or if I had a threshold alpha further to the right, I'd have to have less mass out there, because then I'd have to balance it keeping at 0. Okay, and so this describes this sort of property. Okay, so this is why the property like this is true. Okay, this, hopefully for some of you, this argument made sense. Okay, okay, good. So let's go through a simple example of applying this. Here, okay, so I've got an example here. Let's say I have a random variable R, which is the rain in in Salt Lake City in June, and let's say this is in millimeters. Okay, so I want to say what's the expected value of expected millimeters of rain we get in Salt Lake City. I chose millimeters because the approximate right value actually comes out with easier to process numbers. And we know that the rain must be greater or equal than 0, right? I can't have a negative amount of rain, although sometimes at least maybe in June this year, it felt like the amount of rain was negative. But the expected value of R, if you look this up, it's about 20 millimeters. Okay, so this is what I know about the rain in Salt Lake City in June, approximately. We can kind of look at historical data. You say, okay, let's say the expected value is 20 millimeters, and I don't know anything else about this, right? I'd like to understand what is the probability that the rain is greater or equal to 50 millimeters in June. Okay, it can't be less than 0, and the expected value has to be 20 millimeters. That's kind of the, let's say there really was a probability distribution. This is based on historic data, but typically we do something like this. Okay, so we would say, well, that's expected value of rain divided by 50, and they're both in millimeters, so the units here are canceling. Okay, and this is equal to 20 over 50 and 0.4. So 40% of the time, I would see more than, no more than 40% of the time would I see more than 50 millimeters of rain. Okay, it's an upper bound. It might be that this answer is actually less. That's actually less than 40% of the time I see less than 50 millimeters. But if this is all I know, this is the best bound I can get. Okay, so I'd say, well, just knowing that the rain has to be positive and that the expected amount of rain is 20 millimeters, I say, well, the probability of seeing more than 50 millimeters cannot be more than 40%. So it's, okay. Good. So this is an example of one of these tail bounds. This is a kind of a simple example. Okay, this basically makes sense. Okay, it hasn't gotten interesting yet because I haven't been able to combine multiple of these random variables. And the Markov inequality does not really let me do that very much. Okay, the next ones will be designed more to combine multiple random variables. So we'll go through a couple more and we'll see how the constant, as you get more evidence, more readings of something, you can get a better and better estimate. Okay. The second inequality is called Chebyshev's inequality. These are mainly named after some Russian mathematicians. I think they're all Russian. And so this one again has we'll start with the single random variable x. Okay. And now we know, what do we know about x? We know the expected value of x is equal to mu, and we know the variance of x is equal to, let's say, sigma squared. So these are the two things that we know now. Instead of, again, we know the expected value, but we also know the variance here. But we don't know that it has to be greater than 0. So we could be dealing with some quantity that might be 0 now, or might take on some values which are so negative, right? Like the average deviation in the height of like the Salt Lake, that from the amount it changes in June might be some value which is negative, it might be a value which is positive, right? So we don't necessarily have a lower bound on. So okay, and then given this, for any I'll directly say with epsilon, for any epsilon, we'll get a bound that looks like x minus the expected value of x, absolute value greater or equal to epsilon, right? So this is going to be less than or equal to some term which is going to be delta. This is exactly this pack bound language is now the variance of x divided by epsilon squared. Okay, so this is now the Chebyshev inequality, and this is directly looking like this pack bound I said these bounds would tend to look like, where it's again, I have the error tolerance epsilon, and then this is and this is equal to delta, and this right, and this delta is this probability of failure, probability outside the error tolerance. Okay. All right, so what is the I think the most notable difference here is that, and the thing to point out is that now the right-hand side, the value of delta decreases at a quadratic rate as epsilon is increasing as well. So if I allow more error tolerance, the probability of failure goes down at a faster rate than before. Before it was basically, this was a linear function of epsilon. And it had this other term, which was that was balancing it out. So it's not, as I make my error tolerance get bigger, the probability of failure does not go down as quickly here. Where here it's going down at basically a rate which is linear once it gets large enough, and this one's going down at a rate which is so quadratic. Okay, so this one ends up as you get further into the tail, this one drives a probability of failure down smaller and smaller. So if I want a small probability of being outside the error range, then this one will be able to go out and get to that small probability of the tails of the distribution more, so more quickly. Okay. Okay. Let's look now at this example again with the rain. Let's see if I can do it up here. Again, R is going to be the rain in the SLC rain in June. Okay, and we're going to have let's say we have the expected value of R again equals 20 millimeters. Okay, but now let's say we have something about the variance of the rain. And these are numbers I'm making up just to show an example. Say the variance of the rain is going to be 9 millimeters squared. Okay, so if we have a different set of information, we know the rain is greater than 0, but we're not going to use that here. We're only using this bound on the variance of the rain every June. Let's say it's a pretty tight variance. You know, quite possibly in some places where the rain is more consistent, that might be the right value. Okay, so now if we go through this, so the Chebyshev inequality, I want to know the probability that the rain is greater than 50 millimeters. Well, I can convert this into this is going to be less than or equal to the probability that the difference, the rain minus the expected value of R is greater than 30. Okay, I've done two things here. One is just an equality operation. I subtracted the expected value from both sides. Okay, so now the 50 becomes a 30 because I subtracted 20 from both sides. The second thing I did is I added the absolute values here, right? I added these absolute values here, and that led to this inequality here. Now I'm saying I'm asking for something a bit stronger even. I'm bounding the probability it's greater than 50. Now I'm saying I'm bounding the probability it's either going to be above 50 or less than 10, right? Remember that the expected value, or I guess, or less than, so negative 10, right? The expected value of R equals 20, and I'm allowed to go out 30 in either direction, right? This number is 50, and this number is negative 10. And well, in this case, there's some underlying probability distribution that probably should not go below 0 here, okay? But it might go above 50. Now this bound doesn't know that. It doesn't know it can't go below 0, but so I'm just going to use this version with the expected value. There are one-sided versions of this bound that are, roughly better by a factor 2, but I'm not going to work through those. They're not always exactly a factor 2. So we'll just, whenever we use these in class, we'll use the ones that go through the expected value. Sorry, the absolute value term here. And this will just simplify the analysis we do, but in general, you might care about this like a factor 2 where I don't, I know it's not less than 0, so I don't care about this left-hand side. But here, I'm only kind of worrying about here, or if there was something less than minus 10 on either side. Okay, so that gives me an upper bound here, but I'm going to get another kind of inequality when I apply the Chebyshev bound anyways. So the fact I got inequality here isn't really that big of a difference. Okay, now let's plug in these values. Now I just need to apply the Chebyshev inequality. Okay, and this I'm going to plug in the variance, which is 9 millimeters squared, divided by epsilon, in this case, which is 30 millimeters squared. sorry, not, what is it? Oh, yeah, is the, oh no, it's not, epsilon now is 30, and I'm doing 30 squared. Okay, so it's 30 millimeters squared. And notice now the units are canceling. So I have a millimeter squared divided by a millimeter squared. Okay, but now I've got 9 divided by 30 squared. 30 squared is going to be, so 900, right? So this is equal to 0. So 9 divided by 900 is 0.01. Okay? So now I say the probability, given that if I know the variance is 9 millimeters squared, which means the standard deviation is 3 millimeters, right? It's a pretty narrow distribution here. Then I can say, well, the probability of having more than 50 millimeters rain in June is less than 1%, right? This 1% here, 1% probability, let's make this in green to lines up. This 1% probability is now much smaller than 40% probability, right? So if I have this different, in this case, information that gives me a much tighter bound, then I'm able to get a much smaller kind of a probability of being out, outside this region I want to bound for. Yeah. Okay. Okay. What's cool about this Chebyshev inequality is that I can get better as I get more random variables. Okay, so let's say now, okay, now I've got a case where I have x1, x2 up to xn, and each xi is from the same distribution f, right? And I know the expected value of xi is equal to mu, and the variance of xi is equal to sigma squared. Okay, so now I have a whole bunch of these, and I want to understand something about, again, x bar. Right? Okay, so what's cool is now we know that the expected value of x bar is equal to mu. It's the same. This is by the central limit theorem, or linearity of expectation, and that the variance of x bar is going to be equal to sigma squared divided by n. Okay, so now, just by kind of using this fact from the central limit theorem, I can get a bound which is going to be improved. So now I can say that the probability of x bar minus the expected value of x bar is greater than epsilon, is going to be less than the variance of x bar divided by epsilon squared, which in this case is going to be sigma squared divided by n epsilon squared. Okay, so before I didn't have this, the key difference here is this divided through by n. Right now, as I get n of these random variables that I'm averaging together, my probability of getting outside of a range is going down linearly also with the number of random variables I get. Okay, so I'm also getting a smaller and smaller tail bound, smaller probability of getting outside my error tolerance that decreases linearly with the number of random variables I'm averaging together. Okay, so again, this is kind of a more concrete way of using the central limit theorem here. Okay, so now I can not just say, well, how well is it converging to a normal distribution, but I'm saying, well, that probability of being outside of my error tolerance is going down, and I can quantify that in this way now. All right. Yeah, and so this again is going to be kind of the basis of a lot of our analysis we're going to do. So Did the Chebyshev inequality give us a conclusion along the lines of the chance that the rainfall exceeds 50 millimeters is not greater than, yeah, great. So, yeah, is not greater than 0.01%. Yes, that is a correct way of reading this. Great. Now, if we were to get, okay, great. So kind of this example will not work quite as well with the rainfall. Let me. So yeah, maybe let me start with part of an example, and then we'll revisit it with the final inequality that we're going to do. Let's start with. Let's do an example here where we're going to have a where we're going to have a a fair die, and I want to have t as a random variable that I roll a 3, or it's going to be kind of not exactly that I roll 3, basically. So t is going to be equal to 1 if the die is a 3 and 0 otherwise. Okay, so I'm going to get, think of, I get 1 point if it's a 3, and I get 0 points if it's not a 3 here. Okay, and I want to roll this die for for a bunch of times and say, what's the probability I got so many 3s? Okay, so I know that the probability of getting 1 3 is 1/6. It's a fair die, right? So this is with probability 1/6, right? So I want to ask, what's the, yeah, let's roll roll die n equals, let's do 120 times. Okay, and let's say t is going to be equal to the number of times I roll a 3. Okay, so the number of times I roll a 3. So the expected number of times I roll a 3, I know the expected t is equal to 20, right? All right, and so I want to say, what's the probability that t is greater than 40? I want to get an upper bound of this probability. So I want to upper bound the probability t is greater than 40. Okay, and now with dice, you can calculate this exactly, right? But it's you could work out this exactly. We're just going to get an upper bound in this probability. That's all we're going to care about. Okay, so I want to say that this is going to be less than some quantity here. Okay, and I know that with a die like this, that the variance of a single roll, let's say call this ti, of a single roll of this dice. So t now is just going to be the sum over I of these ti. This single roll of these is going to be 5 over 36. Turns out if you calculate the variance, it's going to be this. Okay, so we can plug this into the the Chebyshev inequality. And well, okay, so I first need to convert it. So I say the probability that t minus the expected value, which is 20, is less than 20, right? So this quantity again gives an upper bound. I've added absolute values. I've subtracted 20 from both of the sides. oh, is probably it's greater than 20. Okay, so this is the left-hand side of the Chebyshev inequality, and I can bound this based on the variance of Ti divided by n divided by epsilon squared. In this case, epsilon squared is going to be 20 squared. Okay, and this will be, let's see, 5 over 36 divided by 120 times 400. Okay, and well, you just have to trust me. This will be 0.042 about. Let me write that a bit larger. Okay, so 0.042, so about 4%. The probability of rolling more than 40 of the threes is bounded by about 4%, means about 42 times out of 1,000 if you do these calculations. Okay, so this is an application of the Chebyshev random variable, but now I'm doing this n times, right? Because I had the variance of a single roll, I can divide that by the number of trials, which is 120, and that the difference here was 20. I can apply that directly here. And now I didn't use the didn't use the average here. I used this sum, but this still works here. Yeah.
Can you go over again how you get epsilon?
Yeah. So 20 is just this term here from the.
Where does that come from?
So yeah. So I got that t is greater than 40, and I can replace this by t minus 20 is greater than 20. I subtracted 20 from both sides. So if I subtract 20 from both sides, then I get t minus 20 on the left, which is t minus the expected value of t. This is expected value of t is what is going on here, right? So I want to subtract the expected value from both sides. I knew that was 20, so I did this to get what this left-hand side is, the right form of the left-hand side. Yeah, right. And in these questions, you may not, it may not initially be posed exactly in this form, so you often need to use a little bit of algebra to convert it into this form, and then you can apply one of these bounds. Great. So if I had more rolls, and I was trying to kind of get twice the expected value, right, that same rate, then this probably should go down because everything should pretty much look the same, but that n would increase here. Okay. Right. I want to go through one more of these inequalities. And this one we'll do one more of these, and then we'll kind of summarize and comment on these and talk about kind of how to decide how to use these. Okay. This is called the Chernoff-Hoeffding inequality. Okay, and so this one, I guess there are different bounds invented by Chernoff and Hoeffding and probably also Azuma, and they all take similar forms, and I've written down what I think is kind of a simplified form that kind of combines these. It's a bit easier to use. Okay, so now this one explicitly states that I have x1 up to xn, and these are random variables for each xi. These are each from, let's say, their IID from some unknown distribution here. Okay, You really only need the independence, but the form is more complicated if you don't have that they're from the same distribution. So but it's important that these are independent, or it turned out they can be so negatively dependent if you know what that is. And this still basically works. Okay, and so I have now two properties. I know the expected value of xi, that's some quantity mu, which I'm given. And I also know something different here, that there's some range AB. I know it's in some range. We had something similar with the Markov inequality, where we knew that A was 0, but we didn't have an upper bound. Now we have an upper and a lower bound here, and I'll typically use delta is some difference between B and A. So I know that there's some range of values. It must be within this fixed range. Okay? And so this is a little bit stronger condition. There's a more there's a different way of explaining this through like a bunch of moment analysis that that you can get a slightly stronger statement of this bound with it instead of using something about all the moments. But this one is much easier to process and is almost always just as useful. Okay, careful where I put my weight. Okay, and now again we want to look at, we explicitly with this bound, it's about an average of these random variables. We know it's the same expected value, and I guess we know the average is also in this range, but we won't use that property. Okay, and so now for any epsilon greater than 0, we're going to state the probability that x bar minus the expected value of x bar, right, is greater than epsilon, right? This is the left-hand side of a packed bound. The right-hand side is now, which is our term delta, is 2x, and this is again the e to some power, right, minus 2 epsilon squared n divided by, so delta squared. Okay, so this looks a bit different. Now is an exponential on the right-hand side here. Okay, and again, this quantity is our delta, our probability of failure that we would like to bound. Okay, and so what this is kind of this relationship between epsilon and n is basically the same as the Chernoff bound. Okay, I get epsilon squared times n. Remember, there's a negative here, right? There's a negative in front here, so this is, it's 1 over e to something. Okay, but if I want to trade off between epsilon and n, this relationship is about the same here. So my error tolerance is a function of n, and I'll write this out in a way that's clear. But the big difference here is this is kind of that we have this exponential form here. And this is going to drive the probability of failure to go down exponentially fast, right? As I get more data, as n increases, the probability of failure goes down exponentially fast. As my error tolerance increases, the probability of failure goes down exponentially fast. Okay, and so this is kind of gives you much tighter tails here as you get either more data or you increase your error tolerance. Okay. But applying is, basically just the same. It just looks more complicated. Once you have this form, and I have this different understanding of the random variables, I have not just the variance, but I have a full upper and lower bound on these things. Okay. So if we started with this just kind of would, it's hard to conceptualize what's going on here, because you have to think about this in terms of this packed bound, right? I have an error tolerance and a probability of failure, and then I have a really complicated right-hand side here, but it's just a formula. Okay, it's just a formula you're going to plug some numbers into. Once you can arrange stuff so the left-hand side looks like you want to, then you can apply any of these bounds. You just plug the values you need to in. Okay? Okay, so let's go, now that we've seen this, right, let's put a circle, a box around this guy. It's important. Okay, so once we have this, let's go and apply this to this same dice example with the rolling threes. Okay, let's go and apply the Chernoff-Hoeffding bound now with the example with the dice. Again, I'm going to have TI equals 1 with probability 1/6 and 0, 0 otherwise. So I know the expected value of TI is going to equal to 1/6, and the variance of TI is equal to 5 over 36. Okay. Okay, and now I'm interested in T, and now I'll write T bar, which is 1 over n of TI, and we'll set n again equals 120. Okay, 120 rolls the dice, and now I want to know the probability that n times T bar is greater than 40, right? Remember, T, I said T before, just so my notation is consistent, is going to be the number of threes. So this is equal to T bar times n. Okay, because okay, so this is the same problem we had before. Okay, and I'm going to convert this, I'm going to divide through by n. Okay, so this is going to be equal to the probability that T bar is greater than 1/3, because n was 120. Okay, and now I'm going to again subtract. Let's do this in a few steps. I'm going to subtract 1/6, the expected value from both sides. The T bar minus expected value of T bar greater than 1/6, right? Because using the expected value of T of TI is 1/6. Okay. And now I'm going to say that this is less than or equal to the probability of T bar minus expected value of T bar absolute value greater than 1/6, if I can write that clearly. Okay. Okay. And so now I want to use the Chernoff-Hoeffding bound to get an upper bound on this. Okay, so now we'll apply the Chernoff-Hoeffding. Okay, and we're going to get 2 times the expected value, or not the exponent, e to some power of minus, let's see if I can remember this. This can be epsilon squared times n over delta squared, right? Okay, what was delta squared? Okay, who can tell me what is delta or delta squared here? Do you remember what delta was? Delta is the difference between the maximum and the minimum values the random variable can take. So it's not 5. It's the random variable. Remember, the random variable is TI, right? It's described up here at the top. This is my random variable. So it can take values either.
Are you talking about the entire distribution or one specific?
Yeah, so a single TI, a single random variable. Yeah, so it's, yeah, A is 0 and B is 1. So delta is 1. Okay, so great. So this implies that delta equals 1 here. Okay, and delta squared is 1. Actually, a very common place to apply these Chernoff-Hoeffding random variables is when you have binary random variables. Yeah, like this. Great, thank you. 2 epsilon squared, great, good. Okay, so this delta is 1, n is 120, and epsilon is what? What is epsilon here? Let's do, what is epsilon? Is 1/6. Yep, great. So so now we can plug all of this in. This is equal to 2 e to the power negative 2 1/6 squared times 120 divided by 1 squared. Okay. Okay. This is equal to 2 e to the power. Let's just so you can see how this looks like. 2 over 36 is 118 times 120, right, divided by 1. And this is about, I guess this is e to the negative 20 over 2, e to the negative 20 over 3. This is about 0.0026. Okay, so now you can say, I'll write this, I think on Zoom. When this goes on YouTube, you won't be able to see the bottom right-hand corner, 0.26 here. So now about 3 out of 1,000. I went from 42 out of 1,000 to about 3 out of 1,000. Okay, so this gives me a tighter bound. Okay, and as if n, the number of trials goes up exponentially, or my error tolerance, I went up to say, instead, did this occur more than 40 times? Did this occur more than 45 times or 50 times? This probably is going to go down very quickly. Okay, and there's another example we can go through if you want, where, and for instance, in the book, that goes and shows how this gets down to like a extremely small number in an example. I tried to put the Markov inequality, Chebyshev, and Chernoff-Hoeffding together in one example, and you can see some of the differences in between them. So kind of once you kind of conceptualize what this form means or these other forms mean, kind of applying them is a matter of translating your problem into this packed bound on the left-hand side, and then doing some algebra. Okay, so they aren't that hard to use once you kind of understand them. It looks kind of really messy, kind of following the examples is, not the most exciting calculations we'll do in this class, but I wanted to work through them for you. And you'll do some of these in your homework assignments. I think these are important because they show you how to kind of really make concrete what this central limit theorem is saying in a useful way. And a lot of bounds and analysis you'll see in machine learning and data mining sort of papers are going to be going through often one of these inequalities to say the error is not too bad most of the time. Okay, so that's kind of, so you'll see bounds that look like this, and this kind of gives you an insight into where they're coming from. The proofs of the Chernoff-Hoeffding and so the Chebyshev actually rely on the Markov inequality. So if you understand how this Markov inequality proof worked, you kind of do something similar, but you have to plug the variance inside of the algebra someplace for the Chebyshev. You have to do all the moments, like the moments of a distribution are the mean, the variance, and then like the skew and the jerk. And these are the the difference from the mean to a higher order power. And if you have all that information, then you can get the Chernoff-Hoeffding bound. And then if you simplify it, you can get it so it just depends on this delta term. I like this form. It's much easier to work with. There are slightly tighter versions of this that deal with other properties of the distribution, and maybe they're one-sided, so you can kind of get rid of this factor 2 in front here, but it's not exactly. They're a little bit different on the upper bound and the lower bound side. So I didn't want to write all that out. This is a pretty general purpose bound, and the result here, right, this is not the best result I could possibly get. I can probably get about a factor 2 better by not doing this first inequality here where I put on the absolute values. Right? I could probably get about a factor 2 better. In this class, we're not going to worry about that. We're always going to go through the version with absolute values just to simplify your life here. And typically, you want to get some sort of asymptotic bound. I actually typically want to leave it in a form that looks closer like this. Okay, so yeah, so let's kind of, one thing to do to compare these things is I want to get, so at the end here, I got this bound that was 2 times exponential minus 2 epsilon squared n over delta squared. And this was equal to lowercase delta, my probability of failure. One useful way to understand this is from the Chernoff-Hoeffding bound. And one useful way to understand this is, let's say I'm told I have an error tolerance, I have a probability of failure I'm willing to accept. So now I'm given error, so tolerance, epsilon, and a acceptable probability of failure delta, and I want to know how many samples do I need, right? I want to think of this as a, error tolerance as some, like a fraction of 3s that I got, and the probability of failure is the probability I got more than this fraction. So, it could be, for instance, and right, I could say this is equal to a 1/10 probability, right? It's supposed to be 1/6, and I got 1/6 plus 1/10, and the probability of failure equals 0. You do something like 0.05. So 5% I got worse than that error bound. So let's say I'm given it this way, and this is how I like to write the analysis when I do analysis of algorithms. A user tells me how much error tolerance they're willing to accept and their probability of failure they're willing to accept. How many samples do I need to take, right? A lot of statisticians tend to write it, well, they leave it in this form here at the top. They just say, well, you can figure it out from yourself. It's converging. But I like to calculate, solve for n. How big of a sample do I actually need? Okay, so we can just do some algebra. Okay, and we can do x, and I'll just go through this carefully because there are a couple of steps where it's easy to make mistakes, and hopefully I won't. But if I do, please catch me. Okay, so I divide by 2. Okay, now I'm going to actually do it's easier to do this step here, although this is a little bit less intuitive, equals 2 over delta. Okay, I've taken out the minus sign from the exponential. That's e to some power. Now that means I'm actually 1 over e to some negative power. That's actually 1 over e to that power. So I can take the minus out and turn this guy upside down. Take the 1 over that. Okay, now I can take the natural log of both sides. Equals natural log of 2 over delta. Now it's easy to solve for n. I can say n is equal to delta squared 2 epsilon squared natural log of 2 over delta. Okay, so what this is saying is that as as the error tolerance goes up, as I gain more error tolerance, the number of samples I need goes down. So if the error tolerance goes down, I need more samples. Okay, and this 1 over epsilon squared, this rate of going down is something that you see in is the right bound. You can see this experimentally. It shows up. It's kind of a very natural bound. The amount of error I get, or the error I'm willing to tolerate, you take that 1 over that error squared. That gives you the number of samples you need to see. So this is a very common thing to see. And now the probability of failure, as that gets smaller, well, that's not a big deal now. It's inside of a log, right? So for every kind of every time it's kind of that's decreasing by a factor e in this case, right? But think of say decreasing by say a factor 2, right? Then I need one additional kind of that log n goes up by 1, an additive 1. Now that's multiplied by this 1 over epsilon squared term, but kind of it's that log term is kind of I can drive that probability of failure down exponentially fast. Okay, it's useful. Now let's do the same thing here with the Chebyshev bound as well. Now I'm going to have that. Remember what the Chebyshev bound was. It was the variance. Let's just write this as sigma squared. The variance over n epsilon squared. This is equal to delta, right? This was the right-hand side of the Chebyshev inequality instead now, right? Remember this? This is when I had n random variables because I can divide the variance by n. That was the variance over epsilon squared. Okay, so now this is easier to solve for delta. To solve for the value n here. Now I get n is equal to, let's see, I can get n delta equals sigma squared, epsilon squared, n is equal to sigma squared over epsilon squared times delta. Okay, great. So what's common in these? I get this n over epsilon squared. I get n over epsilon squared. This is the same, right? This is the right rate for as the error tolerance grows, or the error tolerance shrinks, how many samples do I need to get? So with the Chebyshev inequality, I'm getting this right rate in terms of the error quality. The error tolerance. As the error tolerance shrink, the number of samples they need. That part is right. What is different is the function between n and 1 over n delta, where in this case it's n. So in the Chernoff-Hoeffding, it's n is proportional to log of 1 over delta, and in the Chebyshev, it's n is proportional to 1 over delta. So if I want the probability of failure to go down, that's where I want to use the Chernoff-Hoeffding bound. I want to really be careful there. So if I say I want something to be true with high probability, you often have very high probability, you want to use the Chernoff-Hoeffding. If I don't care, I just say it's true with some reasonable probability, then the Chebyshev bound is often good enough. Okay, so that's one perspective. I have 1 more minute left. Let me just quickly review that the Markov, this had a 1 random variable. I knew the expected value of x, and I knew that x is greater than 0. With the Chebyshev, I have 1 or n random variable. I know the expected value of each xi, and I know the variance of each xi. And with the Chernoff-Hoeffding, I have n random variable, and I know the expected value, and I know some value delta such that xi is in A, B with delta equals B minus A. Okay, so to apply them, I need to know different information here. And this tells me when I can apply them. And sometimes the random variable, I don't need to know the whole distribution, but I need to know some property of it. This has a bit higher requirement. The Chernoff-Hoeffding is a bit higher requirement than the other ones. The variance might be more than the Markov. Which one works the best? I don't really know until I apply them. They all give me upper bounds on the right quantity, but I don't know which is the best upper bound until I apply them. So you might apply all of them and see which one works the best. And so in your homework, I'll ask you to do that. And just to work through this, just to get familiar with these things. Okay, so we'll move on to linear algebra starting on Thursday. And that will give us a language to talk about high dimensional data, which is really what the backbone of what most of data analysis works with. Okay, we'll stop here.